Hello, my name is Max Kim, and this is my arc length project for the AP Calculus AB course. This is the path that I chose to map out and study. So, this is in Old Japan where I live, and this is not like my exact street, but this is a part of the path I take to walk my dog like every day. And this is just like I thought this was an interesting looking path, and it's like one that I use nearly every day. So that's the significance of it to me. So the first step I did was I rotated this image that's normally oriented, and I made it so that this street, Fred Street, was actually the horizontal x-axis. It corresponded to that, so that it would be easier to graph these as coordinate points in like Desmos, so then I could then study the uh, the regression easier. So after I did that, then I went into Desmos, as you can see here, and I plotted a series of points that corresponds to the measuring tool. As you can see here, if I do here, around the segment's around 800 feet, and that corresponds to these coordinate points. So all of these are in units of feet, and I use that to then in the graph tool, the graph app that Dr. Heitzman and Mr. Wall shared. I use that to then formulate a regression polynomial of eighth order. As you can see here, this is a screenshot that I thought did a really good job at corresponding with a majority of the points, but also without becoming too intricate. Like what happens when you make it, let's say, like a 16th order polynomial, because I had 17 points. Because I wanted to capture the curves. I could have made this like a 17th order or like 16, some crazy number, but I wanted to keep it simple while still capturing the main significant points of this graph. So this is my f of x. This is my regression graph formula. And then what I did to find the arc length, I wanted to find the arc length specifically of this like bend here around like this baseball diamond. So what I did was I had the arc length formula that we learned, a to b integral from a defined from a to b of the square root of 1 plus the derivative squared. So I calculated the derivative here. Um, so then just a matter of plugging it in. And you can see here I got these 2 points from Desmos, because this bend here on Desmos corresponds to this bend here on the actual picture. So then I use these points. So this one starts at 1522 and then it ends at 1615. Those are these points here. So then I just plug that in. I use those for my upper and lower bounds, and then simply plug this into a calculator and got an arc length of this segment highlighted here to be 166.75 feet, which corresponds nearly perfectly with the measuring tool. It got kind of cut off because I had the path selected, so I kind of highlighted the path instead of showing my measurement. But what I did for the measurements, I started here, just connected here, and went along. And then, as you can see here, it came out to around 165 feet, which is right on the money with what we calculated with the arc length of that same segment. And then for the rest, I used the measurement tool, or you could just select the path, and it determines the length of the path. So it's 0.487 miles, or 2,571.36 feet. So yeah, that is my arc length project. I selected the path I used to walk my dog every day nearby my house. And then I plotted the points using Desmos and used graph to come up with an eighth order polynomial to use for the regression. And then from there, I took the derivative, simply solved the arc length formula for this specific bend that I wanted to study, and it corresponded with the real life measurements. And then finally, I figured out the total length of the whole path. Thank you for listening.